Greetings, tree huggers and lovers, I hope still. So we keep going, and today's topic is spanning trees. And let me explain what it is. So here I draw for you already a graph, and what we're now looking for is a tree that's inside the graph, meaning we want to throw out some of the edges, and so that the result is a tree, and a tree that contains all the vertices, right? So for instance, why would we want to care about this thing? So I'm going to very quickly give two examples. They are discussed a little bit more in detail in the book. Suppose, for instance, that this is a system of cities or count places and towns, and these are roads connecting these towns, and in the winter we have to make sure, they want to make sure that these roads are that every town can be reached. So what we want to do is to keep at least one road open between, make sure that from every town that there's a road that leads to the other town. Okay, so in other words, we want a connected graph, right? But you want to by plowing it. I'm talking about here snow, like it's in a very harsh climate, to say these cities like in Alaska or something like that, and you want to you have to plow the snow plowing for these roads, but you don't want to do all roads. You say, okay, this road, fine, it would be nice to have this road, but for instance, this road, say you have to go from here to there. You say, okay, fine, now you're gonna have to drive this way. So if we keep this part, then we don't need that one. Okay, so that is a reason why you would want to do away as little as possible. And if you think about it, if you try to do as little as possible, then you end up with a tree. Everything has still to be reached, right? You should be able to go from one place to another. You don't want to isolate anybody, but if you do this as little as possible, you actually get a tree. We'll see this. Another thing that you could think is this is a network of a computer network, and one of the computers has to send an update to the other computer. Let's say this is the main server, he's got an update, and this has to be now sent to everybody. Now, what this guy can say, okay, I'm going to send it to this guy following this path. I'm going to send it to this guy, I have to do it this way, and this way, and this way. This is a lot of sending that he has to do. Instead, if we have a tree, then he says, okay, I'm going to send everything. He becomes the root of the tree, and then I send everything to my children, and those children send it and pass it along. So it's like you pass the message along from parent to child, and to children and so on, because again, that's assuming that we have a spanning tree. So let's talk about how do we get this. So here is an example. So remember, one of the basic properties of a tree is there's a couple of but a tree for us is a connected graph. But I'm gonna not talk about disconnected graphs too much, so I'm gonna leave that sometime. Tree means no circuit. Okay, that is one thing. The other thing is the number of edges. So I've said that also is the same, that the number of edges plus 1 is the number of vertices. In other words, there's one less edge than there is a vertex. That's another characterization of a tree. That's also useful. And if you think about it, that's the least number, right? If you have 5 vertices, if you want to connect them, there has to be at least 4 connections. Okay, and that would be then a tree. Now, no matter how you connect them, if they're all connected, you have 5 vertices, they're all connected, and you have 4 edges, that must be a tree. That's one of the things. So how do we do this? So one thing is, let's see, if this is not a tree, the graph that I have shown, and why? Because there are circuits. So let's list one of these circuits. So here's a circuit, right? Okay, since we don't want a circuit, I'm going to break it down. And so my algorithm, I will describe 3 different algorithms of finding spanning trees. That might tell you that the reason that there's so many different algorithms is that there is a need for these things. Okay, so for now, please accept it, that this makes sense. We want to find a spanning tree. So perhaps let me say, a spanning tree is a sub graph that is a tree containing all vertices. So a spanning tree of a graph, spanning trees of graphs, of a graph, right? Spanning tree of a graph. That is a subgraph of that graph, meaning some of the edges are there and some of the vertices are there. Well, actually all the vertices are there. So it is a subgraph which has all the vertices, some of the edges, and so that it is a tree. And no, we don't add new edges, of course. Okay, so in other words, our naive approach is, well, if we can remove edges, right? That's what I originally said, right? When we think about this as snow closures in the winter, and you say, okay, we're going to close this road, we can do without the road because there's another way. So, because, see, what is the reason? If you have a path, if there's a circuit, there are two different paths from there to there, say. So in other words, there are two different ways of going from one of the cities on the circuit to the other city of the circuit. So we can do away one of the edges. If we do that, we destroy only one of the paths, and the other path still exists. So that's what we're going to do. So we're going to say, okay, what we will do is we're going to delete edges. So okay, I have this picture now. Perhaps I'll take, I don't want to make a mistake that I sometimes make by losing this. So I'm going to take a copy of this thing. Copy, okay. So now I'm going to start erasing. So I'm saying, okay, this is a circuit. I'm erasing this one. And I keep looking now for circuits. Here's a circuit. So let's erase one. I'm going to erase the top one. It really doesn't matter what I choose, okay. So I see another circuit here. So I'm going to erase the bottom. I'll just randomly erase things. Why not? Here I see another circuit. So let's erase. Let's do the right hand side. This one. Okay. I see a little triangle here. Triangles are always the easiest to spot, right? So here's a triangle. Which one you want to do? We'll do. Okay. I'm going to choose you. So I'm going to choose this guy. Okay, that's gone. Still. Circuits, yes, here I see another circuit here, so this is still a circuit, so I have to erase one of these things, so let me erase this one, okay, alright, so that's no circuit. Am I done? No, I still see a circuit, so here is the circuit, so and any edge in the circuit I can erase, okay, so this is now a lot of choices I have, and it doesn't matter which one I choose, let's pick this one, just to be. And look, I don't have circuits anymore. I mean, it's not immediately clear that I don't have circuits anymore, but it is a tree. Why do I know it's a tree? Well, it's count. Remember, we can use this thing now. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the number of vertices is 13. Well, you remember I do number with the pound sign inside of the, so I guess this is how the book writes it, okay. And how many edges do I have? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You see, exactly one less. That's good news. That means we have a tree. Okay, so this is one algorithm. This is the algorithm that looks for circuits, and once it finds a circuit, it says, okay, one of the edges of the circuit has to go. I don't care which one, it has to go. Okay, and that's it. So we have a tree. Now note that this is not a rooted tree. I can make it a rooted tree, but I don't have to. Okay. The other two algorithms are a little bit more specific. First of all, this is cumbersome because it's not easy to find circuits. Okay, these are small. Again, all the examples that we do are small compared to what real life examples are. If you're doing this with graphs of hundreds of thousands of vertices, that's going to take, if you're going to have to look for circuits, they could be enormously long circuits, right? And then you might be very hard to see one. So this is not a very efficient algorithm. So there are much more efficient algorithms. I'm going to do it on, here is one. So the algorithm that I'm going to do is, there are two types, as I said. The first one is called depth first search. Okay, and I'll explain how it works. First of all, in these ones we're going to make a rooted tree. So we choose a root. So choose a root. We can choose a root whatever we want. I'm going to take a root, let's say F. Okay, this is choice I make, but I'm not saying you have to, and you can do this same problem on another one. So let me make a copy of this thing. I don't need the next one anymore. Copy, so that if I don't mess up. Okay, so what do we do now? In the depth first, so okay, you start drawing the tree actually. So here is F. Oh, sorry. Here is F. That becomes the root. And now you walk in whichever way you want, but let's say it doesn't have to be. You can do whatever you want. Okay, so what I'm doing now is just to make it a little bit more systematic. I'm gonna, because I have alphabetic, I have my vertices are ordered. I order them alphabetically? I do not have to do this. I'm stressing this, but it makes it a bit easier perhaps to explain it if I do it. So I'm gonna add to this. I'm gonna say, okay, I'm gonna think of these things as being ordered, A, B, C, D, E, in this way. So I'm gonna go from my root F to what can I, the lowest vertex can I reach from F? Well, you see the neighbors of F's are D, E, G, and H. So the lowest I can do is D. So then that's what I'm going to do. I'm going to go to D. So I'll go to the side here, to D. So, and let me mark this now. Okay, so I've used this edge. Okay, what's the next one I can go? From D, I can only go to E, right? Or I don't want to return anymore, obviously. So I can go to E. So that's the next thing I do. So let's go this way. So this is E. From E, well, I cannot go to F. Why can I not go to F? Because then I create a circuit. So we're searching for a path as much as we can. We're gonna try to make as long a path as we can without making a circuit, because circuits are not trees. So what I can do therefore is go this way to C. Okay, so this is I have no other choice here, so I go to C. So let's keep going left. That doesn't matter how I go here, right? And now there's still one more choice to do. I can go to A. Okay, so the next one is A. Okay, and from when we reach A, there's nothing we can do anymore. So this is now a very important thing. So we start at root and walk. I'm saying randomly here. I actually walked less randomly in the sense what I walked to the lowest possible neighbor. Okay, so but you can do it randomly. You can just pick any neighbor. Start at root, walk randomly without making a circuit. Okay. Now, at some point, this is not going to work anymore. You see this. I ended in A. If not possible, in other words, if you either create a circuit or you have to return back. Remember, we are doing always simple. I said circuit, but I hope you all understood we are talking about simple circuits, right? You cannot use the edge, no double-edged swords here. Okay. So, if not possible, backtrack. So this is an important concept. Backtrack means retrace your steps, but do not include it anymore. Because remember, I'm not going to make it part of the tree. I'm just going to backtrack. Means I go back to the previous one and see whether I have any other thing that I could have done here. And in this case, yes, I could. The only other thing I could have done is gone to B. So I backtrack, I do the same here. I can go back up to C, and now I can go back to B here. So from C, I can go to B. So now I also have used this. Okay, so it got a little bit crooked. I don't know what happened here with my dot here. My dot is somewhere here. Okay, so all right, so great. What now? Okay, so I'm in B, right? And currently I'm at B. The problem is I cannot do anything anymore. So I have to backtrack. But I cannot do anything there, so I backtrack. So I cannot do anything there, so I backtrack. I cannot do anything there, so I backtrack. Oh, here I reach the point, which actually is my root. Doesn't have to be, but it happens to be my root, where I can do something else. I can either go to H or to G, since I'm taking the alphabetically first, just because, yeah, makes it easier. I'm going to go to G. So this means from F, I've backtracked also. So you backtrack, of course, also on your tree that you're building. So G. From G, I can go to H. So I keep going to H here. Right? From H, alphabetically, I should go back to F, but that will be a circuit. That is not allowed. So this would violate this condition, right? So I can now go to either I or K. So I'm going to I because alphabetically that is the first thing I should do. So I go to I. Okay, so that is this part. But once I'm in I, there's nothing else anymore. It has only degree 1, so it cannot leave it anymore. So I have to backtrack. Backtrack to the next available, that is H. But in H I have still a choice, so I go to K. So I backtrack to H, and now I go to K. And then in K, I have a choice, I go to J. Okay. And now I'm done, because I should have perhaps marked them as well, but you see each vertex is now part of the tree. So, and this is a tree because, well, you see that it's a tree, right? You say, oh, is this always a binary tree? No, not at all. This is just because of this picture, and we'll do another picture shortly. Well, let's do it here. Let's do it perhaps. So the other one I'm going to do, but let me do this one first here. Now, remember, a graph can be given. The nice way of a graph is that it's a picture that is very compact. It has a lot of information in it, but there are other ways. You can also give it as an adjacency matrix. Okay, so this is a new graph, and let's do the same algorithm using this one. So now you don't have the picture, but you can still do it. Okay, let's do. Again, I'm going to pick the root. I'm going to take let's take for root E now. So this is a choice I make. Okay, I make the choice root is E. So you all heard me. Don't ask afterwards where does it come. Why is E the root? Just because I felt like making E the root. All right. So next, what do we do? Well, I go to. I'm in E here, right? So here, let's mark E. I cannot pick E anymore because it's now part of my tree. So let's build my tree. So here's E. Now I take the first neighbor alphabetically. That is B. Okay. So I can go to B. Okay, so I've taken B. Now this means B cannot be taken anymore, so I should also erase it here. Well, I should perhaps erase it everywhere now, and the same with E, right? So let's erase the ones. It's a little bit of bookkeeping here, but let's do this because then we won't run into problems. Okay, I think I erased the B. So B, what is the first thing I can choose alphabetically is an A. Okay, I do that. So I choose A. So this is A now. All the A's are gone. Is this an A? No, this is a D. I think that's a D. Yep, I think I got all the A's. Okay. So I'm in A. Can I do this? Yeah, you still have D. Okay, I'll do D. I'll oblige. So we can go to D. So D is now gone. This is D. Anywhere else? This is D. This one weird thing was a D, I think. Okay. I think I got D too. So now in D, I have a choice. Yes, you still have a choice. H. Okay, so in D we had H here. Here is H. Where else is H? Here's an H. And here's an H. Okay. Alright. I know actually how many H's I should find here, right? Because look, this is where I should look for the H's, like D, I, and K. D, I, and K have an H as neighbor. That's what it says. Okay. Okay. In H, I still have a choice. Oh, okay, good. Let's keep going. I. So here is now I. So in I here, E, H, in J and in K, I should erase the I's. Okay, I did that. Oh, also here. And where else? Oh, and the one that I came from. Okay, so I, one in I. Oh, I can take J. Great. So I can take. Well, perhaps. Oh no. Let's keep going that way. J. Okay, so J. So here is J. J has these two more neighbors. Yeah, okay, I got them. All right. So in J, I can take F. You see, you can go pretty long actually before you need to do anything, right? This is F, so this is F, then there should be in C is an F, and there's an, I have a feeling I didn't, oh, here's one more F. Okay, where am I? I'm in F. In F I can take C, all right, I'll take C. Okay, so C, where am I doing? C, right, C here, C, one C, two C's, where's my third C? Oh no, there's two C's, okay. So where am I? I'm C. Oh, I don't have anything anymore. I cannot go to anything. Why not? Because if I would go to any of those B or F's, notice what would this B result into if I go to the two possibilities of C. I could go this way or could go this way. Each one would create a circuit. Well, this would even be a very bad thing, right? But this would be a circuit. So none are allowed anymore. So now I have to backtrack. Okay, so we have to backtrack now. So from C we go back to F. In F I still had a choice, G. Okay, so this becomes G here now. So we now going to have to erase G's. Another G here. G had three. Yeah, okay. In G I have a choice. I can take L. So okay, I'm going to go L here. So sorry, L is now out. L, where is L? Oh, L has only one neighbor, so in L I have no choice. I have to backtrack. Okay? So backtracking, how do I backtrack? On my tree now. I go back to G. In G, did I have choices? No. Go back to F. Did I have choices in F left? No. In J, did I have choices in J? No. In I, do I have choices? Ah, yeah, K. I can choose K then. Okay, I'm going to choose K here. Okay, here is K. So now we have to get rid of K. K has three neighbors. 1, 2, and 3. Okay. And in K I can take M. So I take M. Okay, let's take it out. M. Oh, look. All these are now colored in, meaning they all been used, they all been visited if you want. And so this is now my tree. Now, okay, why is this called? This is called depth first. And particularly what you see is what happens is these are rather deep in the sense of many levels, right? So we go really deep into the thing. And so what we get here, so here are very long paths, for instance, that we would get into this graph. We haven't drawn the graph yet. This graph actually has a picture in the book. It's one of the, if you wanna double check it, I'll put in the. This is the graph, unless I made a mistake, but I don't think so. I think it is figure 9. This is figure 9 from the book, on page 790. Yeah, okay. But I wanted to show you can do it as well on an adjacency table list than on a thing. Now, I made one little silly mistake. I should have... because I want to do this now again on, okay, you see that is where things are going to go wrong. I want to do the second algorithm and I want to use it also this way. That was E, right? I should have made a copy. I made so many copies and then this one I forgot to make a copy. Not very smart, was I? Okay. What was that? I don't even know. C, okay. Let's try again. No, one more time. Yep. I should check whether there's a way of erasing only one type of color. That would be so much easier, right? I'll research it later. I'm not gonna do it now. Okay, here we go. All right, great. Okay, so I'll keep this tree for now. I'm not going to be able to move it. Okay, I'll copy. No, let me leave this now. Let's go back to this case here. So that was depth first. And so what I now want to do is, okay, I'll make a copy of this guy then. Might still have that copy, but... oh, okay, I should also erase then the path that I have. I'll explain now the next algorithm. Okay, so I also have to do this one. what was this? Okay, let's leave that little orange there, that's okay. Cannot, this is like, you know, what is this, operations game? Oh, I see, I'm not even in writing. Okay, and this one I'm not going to be able to do, so just gonna write B. Okay, so here we have it again. And yeah, I want to make a copy, I'll copy it and put it down there. No, I'm going to move it down there. I don't want to lose the tree that we had, but I want to move this back here. So what is now the other option is breadth first. Breadth in as in broad, in wide. So depth first, okay, DFS, and this is BFS. And what you will see is, so the tree that I had the previous time, I took root F. I'm going to take the same root. So let's take root F again. And so we have root F. Okay, so what do we do? Now what we're going to do, instead of keep making a longer paths, I'm going to take as much as I can around F. So I take F, this is my root here, and I'm going to take all the neighbors of F, all of them. So that is D, E, G, and H. So D, E, G, and H. So let's now mark this. I'll do it in a different color that you perhaps see that is a difference from. I take D, F, G, and H. Okay. And then I take the children and do the same thing. Keep repeating as if I can. So let's see what we can do here. In D, I'm in D here. What can I do in D? Well, in D, the only thing that I can do is that I've not done yet. So definitely I'm not going to consider this. But this one is also not allowed because that would create a circuit. So in D, I cannot do anything. In E, I still have one more neighbor left, C. So I can use this one. There's only one neighbor left, so there's only that what I can do. That is C here. Okay. And let's go to G now. What can I do in G? In G, the only thing I can choose is H, but that would create a circuit. So also in G, I cannot do anything. But in H, I can take I and K. I can take both. So it allows you to take many more vertices at once. Right? Or edges at once, it depends on, yeah. So I and K. Okay? So we should perhaps mark already that D is a leaf and G is a leaf, right? I couldn't do anything anymore there, so we have done this. Okay, we finished that level. Let's go to the next level, C. At C, I have two neighbors that I can choose, right? At simultaneous, now you could say which one goes where, that doesn't matter. We're not making it in an ordered tree anymore. In the depth first, the first case that we did, the DFS case, we had an ordering that we used. We didn't have to, but we used it. It made it easier. Here, it doesn't make, you could still do that. You can still list them in the same ordering, so which I kind of do automatically, I guess. But it's, again, we have the choice. So we have A and B. Let's mark this, A and B. So now also these guys are out. So yeah, these A and B are now will be leaves, right, that you can see. Okay, but you see now there's only one thing left, right, at K. I and K, sorry, I wrote here the wrong thing, right, not J, but K. Hope that you notice this and were waiting for me patiently to see this too, and then you would, because don't yell at the screen, I'm not hearing you. Okay, so here, so I and K, I repeat, at this point, when I chose this, I had all the possible neighbors were, of course, G and F, but none of these, I couldn't take G because that would create a circuit. I couldn't take F because I already took that one, but I could take these two. Okay, so I remind you, this was the situation before I added this I and K. So this was the situation. The neighbors were F, not allowed. because I have used it, not allowed because it creates a circuit, allowed, allowed. And therefore we have I and K, which I have now. And then finally you see here, this is kind of a bit silly, so I'm just going to put it J here, right? So this is clear, that is the only thing to do. And here we have a spanning tree, which is different from the one that we have here, you see? And what is different, for instance, very clearly different is where this was, we were saying, is this a binary tree? Well, it doesn't have to be a binary tree, but you see its arity is rather slim, but its height is rather high. Its depth, height, right? Yeah, this is a little bit weird, right? The trees are often, the roots are often put in top, which is kind of weird because a tree, that's not how trees grow, okay? Perhaps they grow like that in Australia, but that's not true either. But okay, yeah, you know what I mean. So that image, therefore, we call this the height of the tree. It's kind of the depth of the tree, right? If you look at it this way. But sometimes we write trees in the other way. We write the tree upwards, and then depth makes more sense. I don't know. It's just depth and height are the same, and here also broad and wide. We use in the same sense. You see, this is much broader. In other words, its arity is much bigger, but its depth is less. Because we're trying to spread, trying to take as many neighbors as possible. Okay, let's do it on the other example that we had here, this one. Yeah, just remind you of this picture here. I'll keep it, that we can go back at it, to show you how deep this was, right? How high this was, deep or high, depending on from which perspective you take. Okay, so let's move this down and use this now to do the breadth first algorithm. Okay, I'll do it here. So we do breadth first search, okay, with the same root. The root that we had was this time E. Yeah? So we keep the same root as in the previous case, because I want to show you that looks differently, the tree. Okay, I choose E. So what do? We take all the neighbors of E. Well, B, D, F, and I. So this is B, D, F, and I. Okay, so let's mark this. I'll do this in red perhaps. So we took E already. We now take B, D, F, and I. B, D, F, and I. So that means what is out? B and D are out. B, D, F, and I. 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 I hope I didn't forget any. We'll see. Well, hopefully we'll notice it. I don't really need to do this side here. I need to keep track here, of course. I need to see what I have done. Okay, so we go to the children now. Okay, child number 1. What you can do? Oh, A, C, and E. All of these are possible. So let's take them all. A, C, and E. And you see I keep using the alphabetic order, but I don't need to do that. I just want to stress that. So A, C, and E. Oh no! Oh! I forgot to. Oh! Shoo! You see what I did? E. I have E already. So in fact, in other words, what I'm doing is not allowed, right? So sorry. So let's back up a little bit. What did I do wrong? Well, I forgot to scratch out E. That's what I did wrong. I said you don't need to do it on this side. I did it on that side, but I should do it on this side too, because E is the root. I've used it already, right? So I should be a little bit perhaps more careful when I erase things like that here. Okay, so B has now A and C. Now we see better what is going on. So A here and C. So let's erase A and C. A and C, A and C, A and C. I think that's it. Okay, A and C. Good. D. What can we do in D? Well, not much. Only H. Okay, so we do H here. So let's erase H now. H, not that way. I want to erase it this way. H, and H. Okay. F. In F, I have G and J. Okay, G comes here, and J comes there. So G and J. So let's erase G and J. G and J and J and J and G and J and G. Okay. Okay. I hope I have got. Okay. I. I can do K, so I takes adopts, let's say, like adopts the children, right? So I adopts K. So K is now not gone, not this way gone. K is gone, and K is gone. Okay, what is left? Okay, we have done that level. Next level. In A, well, we see what is left, right? Well, let's see. Let's walk through them. Let's do one at a time. A. What in A? Nothing left anymore. C. Nothing left anymore. H. Nothing left anymore. G. L is left there. So here I can take L. So this would be L. So here is L. So L is now gone. Why do you keep doing this? L. Okay. J. Nothing left. And I'm going to continue my children, right? In J, where was I? J, nothing left anymore. In K, I have one child left. M. Well, one leaf left. Well, one edge left. One vertex left. M, so M is gone. I have everything now. So this is my tree. And you see, wider tree, much wider than this one, and much less deep. Okay. So now, the textbook describes algorithms in pseudocode, which I'm not going to do, and it discusses here that this is about O(n) square, where n is the number of vertices, the complexity. So these are tractable problems in the sense that they are, if you remember this from discrete mod 1, O(n) square is polynomial time, so this is not too bad. Okay. Now, how can we use this? And this is backtracking. Backtracking was an important procedure in the first one, right? In depth first, because when we are stuck, we had to backtrack, and that is something that is one has realized that some problems can only solve that way. Now, backtracking is not an efficient method. So let me explain what the situation is. So you're trying to solve a problem, and so you're making a decision tree, and you all the possible choices you can make at any particular point. We have seen decision trees. Somehow game trees are kind of decision trees too, in that sense. And then you go search. You walk in that tree and you see, is it possible or not? And if it's not possible, you say, okay, this solution, this way that I, so suppose, let me put it in a simple version of this. Suppose I want to go from F to J. Okay, I'm start walking, just randomly. I don't know exactly where J is, so start walking. Okay, this. I'll say, oh, I'm stuck, I cannot go. So let's backtrack and let's take this road. I go this road, oh no, that's not works. So I'll go backtrack, no, nothing there. Okay, now this way. You're doing all possible directions you can follow, right? But you have to be systematic, that you don't forget anything, that you don't try the same thing 5 times, and that you skip the possible solution. So this, you say, I keep go as left as I can, okay, and you actually reach J. So yes, that is how backtracking works. So here is a simple example. I will not spend too much time on this. I'll do the other one a little bit longer. It's the example of coloring. So here we have this graph here, and we want to put colors in the graph, so that we want to color the adjacent. Sorry, let me make the picture. So I want to give colors to the different vertices as little as possible, so that no two adjacent vertices have the same color. Now we remember that we did this with 2 colors. If you do 2 colors, this is exactly what, if you can do this, then you get a bipartite graph. Okay, but we didn't talk about more colors, but you can do this for more colors too. It tells you something, but we are not going to discuss coloring problems. I just want to give you this example. How do you do? So you pick an arbitrary thing. Again, this is picking your root basically. So I pick, let's pick this vertex here. And so we have to give names to it, A, B, C, D, and E. So I pick D, okay? And so I'm gonna give D a color. So I make D red, okay? And then I take an, let's see. Yes, in this case, I can take whatever I want. I don't need to even take a neighbor. Okay, I can take any random. I can randomly choose. No, that's not right. Wait, sorry, no, I'm saying it wrong. No, I have to take a neighbor. Sorry, of course, I have to take a neighbor. So I have many choices. I pick one neighbor. So if you want, I'm doing the depth first search. Okay, remember that it's creating paths and see whether you work. Okay, so I'm taking. Let's take E. Okay, now clearly, if I take E, no, let's take. Sorry, let me not take D. Can I start from something else? Let me start from E. Sorry. I'm just doing that because there's more to show if I do it this way. It's a very simple graph, so there's not that much to show. So, okay, E is red. So now I pick any of the neighbors of E. There are two, B or D, right? In depth first, you walk to one of the neighbors, and then from that you walk to another neighbor, and so on, without making circuits. And if you cannot do any more, you backtrack. Remember? Okay, so we go to B. So since this is a neighbor, I have to give it a different color. So I'm going to color this now green. Okay. I want non-adjacent one. So okay, so we should do this here on the thing also. So this is green, and the other one was red. Okay. Now let's take another path. I can take D or I can take A. I'm going to take A just for the fun of it. Okay. I take A, and I'm going to say what colors can I give to A. I cannot give green because it's a neighbor of B. But if I can, I'm going to try to give it red. The color, there are three colors. I don't want to use the third color yet. I postpone as long as I can. So in other words, I put my colors in order. There's a red color first, then is the green color, and then will be the blue color. So I'm almost going to try each time I have a new vertex, I'm going to say which of the colors can I use in that order. I can use red, right? So I'm going to color it red. So I color this red here. Okay, this is now colored red. Okay, so this is now red. And I choose, again, what can I do? C and D are the only two choices, so let's take C. So here is C. Now, if I take C, what colors can I give to C? Oh, I guess I took the wrong mate. Okay, in this case, there's no backtracking really going to happen. Let me take D, sorry. I want to show you how backtracking works. What I told you is you can do this randomly, right? So I'm picking randomly D. Okay, so what can I give to D? Can I give it red? No, I cannot give it red. Can you give it green? No, you cannot give it green because of B here. Look, you have to look at the graph, right? From this it seems like it, but from here you cannot. So what I have to do is I have to use the last color available, so blue. Okay, so I'll put blue. Where is my blue? Here is blue. So this is now blue. So D is blue. Okay, so now pick a neighbor. Oh shoot, it works. I don't have to backtrack. Yeah, in this situation I don't have to backtrack. So because now I can take C and I can give it green. Sorry, I have to choose something that doesn't work. So I'm gonna make a new. Gonna do it again. I want to show you how the backtracking works. So we were able to color it in 3 here. So let's take C. Start with C and give that there for the red color, right? Red color C. Okay, and then the next one I choose is D. So red. So this is still red. D I have to give now green. So this becomes green. So I mean green here. So okay. And now I choose E. I could choose A. I could use B. I'm going to choose E. I just want to follow my. I'm making choices randomly, but there's a reason I took this one. E. What can I give E? Well, the first color I can give E is red. I can give it red, so I'm going to give it red. Okay, remember, always the first choice possible, I'm going to give that. So this becomes E. So what else can I now do? Now I have no choice. I have to take B, right? Because I'm making a path, right? And I cannot, I mean, I cannot backtrack. So the next thing I can do is B. So let's pick B. So I pick B. Okay, so here is B. What color can I give B? Now from the picture you see, red is not available, green is not available because they are adjacent. I have to take blue. Okay, fine, I have blue, so I do that, no problem. So this becomes blue, or I should circle it perhaps. I want to erase it later. So blue, okay, blue. And so now what else can I do? Well, I have to take A, right? I have no choice. So A, but now I'm in trouble. If I take A, it has a blue, a green, and a red neighbor. So A cannot take any of these three colors. So blue is a losing position if you want. I cannot win the game with three colors here. So this is now where I backtrack. So let me point it out here. So there's no further solution. So the next one would be A, but I cannot color this, right? This has no color, A. So I'm not going to write it therefore, so I'm going to say, so there's no, I'm just saying it, let me not write it down, just say it, because otherwise there's too many lines here. So what I do now is at this point I backtrack, and I go back to E, and I say, okay, sorry, I made a mistake in E. So let's backtrack. So that means I'm recanting my choice of B, and in E I say I have to take something else. Well, you cannot, because you can only take B, and D is already chosen. Okay, so I retract my choice of E. I'm retracting that also, E. So in D, now I can choose something else. I'm going to choose B now. Okay, so in D, you choose instead B. Okay, now you say, hey, there's two same B's. Yeah, but for us, this is now considered differently, right? So it's you have to think of this as the labels that these are not the labels of the tree. These are labels of tree, not the names of tree. So this B is different than this B. Why? Because this is the B where C, where the path is red, green, red, blue, and this will be different. Red, green, and now comes something else. Okay, what can I give to B? Let's think about this. At B, I can give already red. I can give it red because that's available. So I'm taking that. Okay, so I'm giving it red. So you see it becomes a different guy. So this is now B. Okay, now what can I choose? I can take A or E. I'm going to take E. Okay, let's take E. What color do you going to give E? I have to give E blue. Right, okay, so I give it blue. So you give it blue, so E becomes blue. But what now? Well, I have to, and E, I cannot do anything anymore. So I have to backtrack now, because I need the spanning tree, right? So this should all be different nodes, and the next one, an E is only D and B, which I have already. So I have to stop here in E, but look, okay, right. So I backtrack to B. There's no choice that in B I could take. No, what I'm trying to say here. No, I'm saying it wrong. When I'm in E, I'm okay because I have not violated anything. The problem is I cannot get to A. So from where can I get to A? Well, I can start over at C again, and here from C I can take A. What's the next color available? Well, I cannot take red because that's C, and also B. I can also not take green because that's this color, but I can give A blue. So I can go here and take A to be blue. Now, I didn't really, I must say, the way I denoted it here in the graph is not really the right thing. In the book, they explain it better. But I don't want to spend too much time on this one. I want to do the n queens problem. So what are we dealing with here? So this is again chess. So this is from chess, and I hope you guys know a little bit of chess, otherwise I have to explain this. So a queen in chess, so a queen, so we have a chessboard, right? Let's take a 5x5 chessboard. I know they are 8x8, but let's take it a bit smaller here. Okay. So my queens, I'm just going to make an X here. So suppose I have a queen here. So when the queen is positioned there, what are the positions she can move in one move? Okay. In other words, which pieces can she capture? There are the pieces that are in the same column. Let's make this red. The same column, in the same row, but also in the same diagonals. The this diagonal, and this diagonal. So pieces that are each of these squares here, so this square, this square, this square, this square, here, 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 and here, can all be, and oh sorry, and these two, all can be captured by the single queen. So if you want to hide from the queen, you have to go in one of these spots here. Now, okay? Now, if you're a pawn, you can go there. But now, the challenge is to put another queen there. So let's put another queen there. So I'm going to put a queen, a second queen. So this is going to be my second queen. So perhaps I should do this in different colors, right? So my first queen was a red queen here. So let's do now a green queen. So I'm going to say, okay, I put a green queen here. So what is that now? What can she capture? Well, she has the following thing that she can capture. Everything in this line, everything in this line, everything in this line, and everything in this line. Okay? So now I have to put yet another queen. Okay, where can that go? Let's make it the blue queen. Well, you see there's still a couple of things free, right? They cannot go in anything that is covered by either the red or the green queen. So I can put my blue queen here. No, let me make it in like this, blue. So here I put my blue queen here. You see that's still a free position. It's still not attacked by any of the two queens that I have so far. What am I attacking now? Well, this queen is attacking everything here, everything here, everything in here. Okay. Still some positions are... I'm going to put another queen in there. Okay, all right, okay. Let's put another queen in there. Let's put a purple queen in there. I put the purple queen. Oh, damn it. Okay. This is what is happening is something that I was not normally don't happen, but it somehow happens. So this is purple, this is purple, oh, this is purple, and this is purple. So there is still one position available, and that is this position here. So this is the gray queen can go here, and she would capture this, this, and this. So what we have found here, and this is not actually what I wanted to do, but it happened. Okay, because it's not an easy problem, I found a solution. This is the 5 queen problem. So n refers to the number of queens and the size of the chessboard. Okay, sorry. So n is the size of the board, and is also the number of queens. So the question is, if you have a 5 by 5, can you put 5 queens so that none of them attacks the other? Now we found a solution. But I was actually very lucky because I randomly chose this, and normally when you do this, it doesn't work. So I want to show you how you solve this problem by backtracking. But 5 is already quite big, and I'm going to do this as a homework problem, but let's do the 4 case to explain this. So how do you do this? We're going to put, we start with an empty board, okay? And each time we're going to build a tree. And the trees will be labeled by chessboards. And in each chessboard, let me see if I can make the paper. No, okay. I'm going to put a queen in the first column. Let's do the columns, okay? Is that what they do? Sorry, let me. Yes, in columns. Okay. So I'm going to put a queen in the. I'm trying to, okay, let me do it and then I'll explain later what I'm doing. So here, I'm going to put a queen here, in the top. I'm going to put a queen here, okay? So this is my child. And now I'm going to put in this thing, try to put a queen in the second column. Now, let's see, what are the positions that I can put without attacking each other? I cannot put it here, I cannot put it here. Clearly, right? You understand why? Because this would attack at this, and this one would attack it. So I can put it either here or there. So let's look at each possibility. So one of the possibilities I can have, so this is the possibility. So what I'm trying to do is I have to be systematic. And so systematic means that I have to follow a rule, make sure that I check out all possible positions. So the first available position in the second column is in the third row, right? So in this level, at this level, so this is, let's call this first column. This is the second column that I'm trying to fill in. And then I go by row. Okay, so now in the third, so now the next level will be the third column, right? This is the third column level. Where can I put in here a queen in the third row? Not here, because this one attacks it. Not here, this attacks it. Not here, this attacks it, this one. Oh, I cannot put anything here. So this is, I cannot go further. If I have a solution, I will be able to put a queen in the first, in the second, in the third, and in the fourth, right? If there is a solution, I should be able to go to level 4. But I'm already stuck at level 3. So what do is I backtrack. I say, okay, this position is not winning, so what else could I have done here? Well, you had another choice here, right? Because what did we do here? So again, the original position is here, and now we have to put a queen either here, here, or here, or here. Now, these two we couldn't do. This position we tried, but it led to nothing, so we're going to have to try this position. Okay, I'm trying this position here. What can we do now? So remember, now in the third column, can I put in the third column a queen? Not here, but I can put her here. I cannot put her here. I cannot put her here. So keep in mind, there's only one position left. So there's only one possible choice here. That is this one. If it works, then we are done. If it doesn't work, we have to start over again. We have to backtrack. So let's see. So we have these two queens, and I said we have to put that queen out there. So what are we still left with? This is taken, this is taken, this is taken, this is taken. So again, this has no solution. Right, so now I'm putting something in the fourth column, right? This would be the level 4, the fourth column. But I cannot do it. So what does that mean? I backtrack. I go to the previous situation. Said, okay, the choice you made, this choice you made is not working. What is your next choice? This is not my next choice. There's no next choice. Okay, so go back up. Okay, so this, what you did, what is the choice that you made here? You put this choice. Well, none of these choices work, so let's go to the next choice. That would be this one, right? Put one row lower. So okay, so we go now to this. Oh, I keep jumping. So I go down here. Oh, crazy. Okay, so here is my thing. Okay, I put my queen here. Okay, what is in the second column, what is the first thing I can do? There's only actually one position. I cannot put it here, cannot put it there, here. I must put it there. So there's only one choice I have. So here is X, I have to put it here. In the third, what can I do? Can I put it here? Yes, not there. But I can put it there. So since we can put it there, let's put it there. Notice it's actually the only place I can put it. I cannot put it here, cannot put it there, cannot put it there. But that is not my concern at the moment. My concern is I can put this. This is the first choice, so I'm going to do this. Okay, so I do this. So here is these two queens. I said here I can put my queen. Let's see whether we have a solution now. Can I put a queen here? No, no. Ah, I can put a queen here, so I found my solution. Okay, here is X, here is X, here is X. And if I put my queen here, she will not attack anybody else or cannot be attacked because it's mutual, right? If one queen can attack the other queen, then vice versa. So that's the backtracking method. Okay, this gives me the solution by doing this systematically. I repeat let me say it one more time, and then I'll leave it to you to do it in homework. I put queens at each level. I have to put a queen in the corresponding column. So this is the first column, second column, and so on. And I look at all possibilities. So of course, what were the possibilities here? There would be 4 possibilities from this empty place, right? I could put it here. I could put her here. I could put her here. I could put it there. So there are 2 more children. But the beauty of this is that I don't have to draw the whole tree. I'm only drawing the tree until I find a solution. Now, in bad case, the worst case scenario is that the solution is actually where the queen has to be in this position. If that's the only position that will work, then it will take me, will have to walk through the whole tree almost before I find the solution. But the hope is that it's kind of somewhere halfway at least, and perhaps even less halfway. And it depends a bit on how many solutions there are. Okay, so that's the idea, is we do this systematically, and then we continue with the second column. Again, the first possible position that is allowed, we put in. This is going to be much more relevant if you do this by 5 by 5. We did find a solution by accident. It's not a solution that you would find if you do the backtracking. So I think it's a homework problem, but if it is not, then I'm going to assign it. So do the 5 by 5 queens problem, but I think it's no problem. Okay. And then finally, the last backtracking thing. So we have a bunch of numbers here. So it's a set of numbers, 31. And I'm going to list them already in descending order, because that's how the thing will work. And the question is, can I find some of these numbers, each using only once, so that the sum is 39? Okay, so it's like you can think of this as a question. Pick these numbers to make 39. You can take as many as you want, but each number you can only take one. Let me show you how this works in backtracking. So, of course, in the beginning we have nothing. We have an empty set. Let me write the empty set like this, the empty set. Okay? And what is the sum then? So I'm going to do the sum. I'll do that in a different color. Let's do it in purple. So at this point, the sum is 0. So purple is the sum. Okay? What I'm going to try to do is to put in as high a number as possible. So again, these are greedy algorithms, by the way. I didn't point that out, but all these are greedy algorithms if you still remember what that means. So I'm going to try to put in 31. So now I put in 31 in my set. I'm going to kind a subset of these numbers, perhaps all of them, but okay, a subset. So 31. What's the sum of 31? Well, that is just 31, right? So that is sorry. So that is the sum is 31 here. Okay, so let's try. We're not on 39 yet, so let's put in a number. Which is the first number I can put in? 27? No. 15? No, because if I put them in, I'm getting too big. So I'm trying to put in as many at each stage. I put in the highest number available that keeps me below the sum, or perhaps equal to it. If I'm equal to it, I'm happy. Then I'm done. I stop. But I'm trying to not exceed it. Okay. I cannot use 27. Well, 31, of course, I've used, so I cannot use it anymore. But 27 I cannot use because that's too big. 15 to make 11. But I can use 7. Okay, so the next play that I can do is, oh, sorry, this should have been black. So now I have 31 and 7. They add up to 38. Okay, let's continue with this game. What's the next thing I can add to this? Well, nothing anymore, because all the other numbers are too big. So this means that this is a losing position. So there's nothing I can do anymore, so I have to backtrack and go here and say, what else could I have done here? Well, instead of adding 7, I could also have added 5. Okay, let's see whether that works. So instead of that, I do 31 and 5. What's the sum? 36. Can I go on now? Well, no, 36, there's nothing, it's too small. So I have to backtrack. But 31, I've exhausted all possibilities. If there are no possibilities anymore, I have to backtrack even higher. Here, of course, I had choices. What was the next choice I could take? The next choice was the next biggest number, was 27. So let's take 27. The sum, of course, is 27 yet. What's the next thing I can take? Can I take 15? No, that would be 42, right? But I can take 11. Okay, I'm going to take 11. That sounds good. I'm going to take 11. So here is, so I have now 27 and 11 that I put together, and that sum, of course, is 38. It's not 39, but I cannot add anything anymore. So no, I have to backtrack. Go back up to 27. Go back one up. Did I have other choices? Yeah, you have other choices. You could also have taken 7. Okay, so let's do that. So we go here. Let's put it here. So I could have done 27 and 7. That would give me 34. Okay. Can I do something here? Yeah, you can add 5, and look at that. You're there. So you have, if I add 5, you get 27, 7, and 5, and that add up to 39. So that is the solution here. And if this would not work, we backtrack again, we keep backtracking. What if we keep backtracking and we never find a solution? Well, then we are guaranteed there is no solution, because there's nothing that says that it works, right? We don't know whether this works. By the way, if you like the game with the matches, you can think this also at the following thing. These are the number of matches you can at each time remove. And this is the number of matches you start with. So you can, rather than summing it up, you can think it's subtracting, right? So you could have worked it that way out. It comes down to the same. And you have the same problem, right? Can I do it so that by taking the right amounts away, that I end up with 0? Now, so again, there are many, many questions, of course, that you can answer. There are homework problems with a bit, where perhaps the search tree is a little bit longer, where you have to do a bit more of backtracking. So this is the application of spanning trees. It might not be immediately clear why are these spanning trees. The backtracking is basically, let me say that the logic is that when we want to do a spanning tree, we used depth first. And in depth first, you are trying to make as long walks as possible until you cannot anymore, and then you backtrack. Okay? So that's the backtracking part. It's just not directly spanning trees, this last part that I did. But the breadth first, we didn't have that. That was the advantage of breadth first, is you just keep finding. And well, in some sense you're also backtracking, but it's different, right? Because you know which levels you still have to work at. So it's a different kind of setup. Backtracking is very common thing, and it's sometimes the best solution. It's not, you see, it's not efficient, because as I said, for instance, in the case of let's say this case, if it was so that the only solution you would get is, suppose the sum was 5, imagine, or say 12. Suppose the sum was 12. It's clear that you can do it with these two, but following this rigorously, you would first have to take, no, 12 is perhaps not a good number. 33, which would be the last 3. Okay, let me do this one perhaps. Let's suppose it was 33. I'm not going to work it out, but I just want to point out what happens here. If the sum is 33, so this would work with the last 3. We know the solution. But see, you would first have to 31 and see that it doesn't work. Then you have to go to 27, see that you cannot do anything at all, because you can, 27, and then you would add 5, and then you would get stuck. So you have to backtrack, and then you see there's nothing else you can do. Now 15, you say, okay, I could 11, okay, and then I could add 7. Oh, that also works. Oh, there are 2 solutions here. But you get what I'm trying to say is, it could be that the solution is all the way at the right-hand side of your tree that you're building, and so you would have to build the whole tree. If the solution is somewhere in the middle, which you see what happens in the average, you kind of have to do only half the work. That's the idea of how backtracking sometimes might work, and sometimes the only way that we have to find solutions. Okay, I'm going to stop here and leave the rest to homework.